So I just want to go through the infinite square well. The infinite square well is essentially you have your well, this is 0 and some distance above 0 a along the x-axis. You have v of x is equal to 0. The energy is 0 in this state. Outside this region here, this is v of x is infinite. So the particle is essentially trapped in this region here. Classically, it would be bouncing between two impenetrable walls. However, we're going to solve this quantum mechanically. So Hamiltonian phi is equal to energy phi. Time independent Schrödinger equation. So phi, the Hamiltonian is negative h bar squared over 2m del squared del x squared. Phi is equal to energy phi. So what we can do is we can introduce a variable k. Actually, we'll make it k squared is going to equal, well, multiply this side by 2m. So we have 2m e divided by negative h bar squared, and that means that del squared phi del x squared is equal to k squared times phi. Now this makes it much easier to solve because we can simply use a sign solution. So phi is equal to sine kx, which means, well, the derivative of that, you take k outside, sine, not sine, cosine, cosine x, and then you take the derivative again, you get negative sine k squared. That. So actually that's not quite what we wanted, but k has a negative thing here, so we can just take that off, and then that that negative will be absorbed by the k and will give us the original, this thing here, essentially. So that's our solution. Now consider that at this point here, I haven't written out the full Hamiltonian. The Hamiltonian is, let me change color just for reference on the side here. The Hamiltonian is negative h squared over 2m grad squared plus v of x, and in this region here v of x is 0, so I've ignored it. However, in this region here v of x is infinite, so the Hamiltonian operated on the wave function, infinite operated on multiplied by the wave function, has to, well, it can either equal infinite, or if the wave function is 0 at that region, it will equal 0. And we can't have an infinite wave function because that would not be normalizable. So the wave function at this region here must be 0, and the same argument can be applied to the region to the point A. So the wave function must be 0 here, and well, 0 all along here and all along here, and must normalize to 1 in this region here. So let's line up in other words, sine kx equals 0 must equal 0, and it already does, so that's fine. But also sine ka, where x equals a, must also equal 0. Thus, ka must equal n pi, where n is any integer multiple. But we've already defined k back here, so how do we justify this? Actually, firstly, this must mean that we have this must mean that k, well, a can be anything. We can define our potential well to be as big or small as we want. So k must equal n pi over a, such that the a cancels and we get sine of n pi at the boundary area. So in other words, the square root of 2me over h bar squared, not squared, sorry. It was squared here, we take the square root, it's no longer squared. So must equal n pi over a. So this is how we get energy quantization of the infinite square well. We can then solve for energy multiplied by h bar and then square it. 2me is going to be equal to n pi h bar of a. I'll just make those, bring this up a bit. N pi h bar over a, and that's all squared to kill the square root. Now we can just divide by 2m, and that can be simplified a whole lot. But then what we get is the quantization expression for En, and this E can be different values, but it must be, it's defined by this. It must be an integer multiple, not quite an integer multiple, it goes with the n squared, but it must be some multiple of this function, such that the wave function is 0 at the boundary condition, and that determines the quantization of the infinite square well. Now, we still need to normalize this wave function such that the probability is equal to 0. Probability is equal to 1. The total probability is equal to 1. But I'll do that separately.